Good morning, everyone. I am Priyanka Sisodia on behalf of Mathematics Department. Know that it is 22nd December. Every year we celebrate this day as National Mathematics Day. It is celebrated to give tribute to the legendary mathematician Srinivas Ramanujan on his birth anniversary, who made great and original contributions in fields like complex analysis, number theory, infinite series, and continued fraction. He is also known as the man who knew infinity. As we are celebrating National Mathematics Week, and this is the third day of our week, and we are honored to have Professor Dr. M.J. Mahan sir as our expert on this very special occasion. While talking about sir, he completed his PhD in mathematics from the University of California. He worked at many well-known institutes, including Institute of Mathematical Sciences, Chennai, Ramakrishnan Mission Vivekananda University, and now presently working at TIFR Mumbai as a dean. He has widely published and presented his research in the area of hyperbolic manifolds and ending combination spaces. And his most notable work is the proof of existence of Cannon-Thurston maps. He is also the author of a book, Maps on Boundaries of Hyperbolic Matrix Spaces. Sir was also invited as a speaker at the International Congress of Mathematicians in 2018 in Rio de Janeiro, and he is also awarded with Shanti Swarup Bhatnagar Award and Infosys Prize for Mathematical Sciences. Now I would like to invite Dr. Mahan sir with the quote, "Mathematicians are near to God." Sir, please address the session.
Please. Yeah, thank you very much for the very kind introduction. Am I audible?
Yes, sir.
Okay, good. So let me start. Yeah, it's a real pleasure. And yeah, I mean, I have very fond memories of visiting Indore a couple of years back. Unfortunately, now because of the COVID, we can't do that. Anyway, so my talk today is just tell me one thing. How much time do I have for this talk?
Sir, you may take your own time as we consider as
so
45 minutes.
Okay, fine. All right. So yeah, so the thing is, my talk will be on shapes and geometry of surfaces. So I'll start off by saying what surfaces are. I mean, what really do we mean and what are we trying to understand? Okay, so when we look around us, the visual information that impinges on our visual sense, this is quite formidable. It's a huge amount of information that comes in. So there's a bewildering multitude of information that comes in. And so, for example, I'll start off with the shape of the Earth. This is a globe, and this is basically what is called a knot in three-dimensional space. But this is a range of shapes which are which impinge on our visual sense. And I mean, once we look at it, I mean, let me just quickly go back again. I mean, and then you'll see that the range of things that's going on is pretty large. Yeah. So this is the kind of range of visual information that impinges on our senses. And the objective, I mean, this is just a very small sample. And what we are trying to do is, at the broadest level, trying to understand all this visual information. All this visual information, I mean, through the human principle of understanding information into classifying dockets called knowledge, that's what we are after. Okay, very good. So how are we going to organize all this information? So this is the problem in front of us. Yeah? So in a very large sense, what we are trying to do is take as raw data all visual information, all visual information available to all human beings, and then classify that into something that is understandable, something that is comprehensible to us, which means we should be able to manipulate this variegated data, this tremendous amount of data, into something that is comprehensible, something that we can communicate from one human being to another, from teachers to students, from researchers to other researchers, and then basically to larger groups of human beings who will be able to run with this information and use it for further enhancement. Okay, so how are we going to organize this information? So we need a formal structure. We need an abstraction. Yeah. So let me go on a quick aside here. Say, for example, and since this is Ramanujan's birthday today, it's important that we at least say something about numbers, because Ramanujan was a number theorist. So what exactly is the kind of classification that we are after? So here is the thing, and I'll just sort of give you a very simple example to show that this capacity for abstraction is something that is common to all human beings, yeah, perhaps to animals as well. So let me just ask a simple question. What about the number 2, or the number 1, or the number 3, or the 7, or 869? These are called natural numbers. The positive integers are called natural numbers. Why? Because they come from nature, which means our visual information abstracted out gives rise to these natural numbers. Question: do we see 2 or 3 or 4 or 869 in nature, the number itself? The number itself is not visible. What do we see? We see 2 people, 2 oranges, 2 beds, 2 chairs, 2 tables, 2 people, 2 fans, etc., etc. What is common to all these things? What is common to 2 fans, 2 chairs, 2 people, 2 ducats, 2 oranges, 2 apples is the number 2. The human mind abstracts out from these concrete 2 apples, 2 oranges, 2 chairs, 2 tables, the number 2. This abstraction is what we give a symbol to and write it down as the number 2. Yeah? Similarly, 1, similarly 869, etc., 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 etc. Which means what? This was probably done very far back when people became settled down as what would human beings do? And they would need to count them. Now, if you count cattle, and then you can't expect them to stay in one place. So what does one do? So one cow enters some, say, pen, and the person who is counting puts a pebble in his hand. The second cow enters, puts a second pebble in his hand. Third cow enters, puts a third pebble in his hand. At the end of the day, after all the cows have entered, instead of counting the cows physically, what the person does is he counts the collection of pebbles in his hand. What this person, this primitive mathematician, is doing is he is instinctively coming up with the notion of an equivalence class. The equivalence class is a number. The number of pebbles and the number of cows are in bijective correspondence, and the cardinality of that set is what is called a number. It is an equivalence class of 2 apples, 2 oranges, 2 fans, 2 chairs, 2 tables is called 2. Yeah. So this capacity for abstraction was there in primitive human beings as well. It's not something that is a special privilege for us today. It was there with other people, but once you have abstracted these numbers out, then you can proceed to understand these things in their own terms. So the abstraction is from nature. The second level when we try to understand these abstractions in their own terms as concrete objects, then what we are doing is proceeding to a second level where these abstract concepts, which refer to something concrete in nature, are being manipulated, are being understood in their own terms. So, this number two, the number system, is an abstraction which comes from nature, which helps us in counting. But once we've abstracted out, then the properties of these things can be studied in their own right. And what we are doing here in today's talk is we shall apply the same And so the question then becomes, what are surfaces? Yeah. And the quick answer is, take any visual data, say you have a chair in front of you. What happens is that when you look at the chair, your view gets obstructed by the surface of the chair. We think of the chair, the brain tells us it is three-dimensional. There's one extra dimension called depth, but we can't see into the chair. We can't see the third dimension inside the chair. What happens is that our view gets obstructed at the surface of the chair, and we look at this two-dimensional thing which is on the surface. So imagine if one was a very small creature, say an ant, crawling on the surface of a chair. What would that ant see? That ant would see around itself a flat two-dimensional object. When it crawled up, let us say, it would again be on the chair, but again, it would look at only a very small region around it, and it would see a locally two-dimensional object. In other words, the ant's view of the world would be of surfaces. Forget ants, human beings, till say 400 years back or 500 years back, we thought of the earth as flat. There is this picture behind me of the Marine Drive in Bombay. The surface of the water looks flat, but we all know from images taken in space, from various other reasoning, that the surface of the earth is actually round. But locally, when we think of ourselves as these small creatures moving around on the surface of the earth, we see the surface of the earth as flat, as something two-dimensional. So our view of the world necessarily gets obstructed on the two-dimensional surface. So when we start off by trying to understand all visual information, what it willy-nilly takes us to is to a more precise understanding of objects which are locally two-dimensional. So that's the first step towards getting this formal structure. What did we start off with? We wanted to understand all visual information. This becomes a little more precise, and we call them things which are locally two-dimensional, which means if we stand at a place and look at the object that we are studying around us, that object is two-dimensional locally. The global shape of the earth is a round sphere. But if we are walking around on a small part of it, it looks like a little patch, like a little two-dimensional thing. This is the reason how charts came into being, how atlases came into being. When you look at a map of the earth, what happens is that a little part of the earth has been taken out, has been mapped into some detail, and that has been drawn as a map on your graph paper, let's say. And that map is what we are studying. We know that it represents some part of the earth. So different parts of the earth are mapped into little two-dimensional pieces. So that's just flat piece of paper on which there's a picture. And that picture is supposed to represent a part of the earth. This is the meaning of the statement that the earth is locally two-dimensional. Okay, so fine. So far we have made one step towards understanding the objects that was our goal to understand, namely all visual information, and we have been able to abstract that out into trying to understand what are locally two-dimensional objects. Now the question is, the other thing, the verb, is we want to understand. What exactly does understanding mean? What do we mean when we say that we understand the number 2 or the number 3? Basically, it means that if you're given a collection of objects, in front of you, you will be able to count, and then you'll be able to say this is some fixed number of objects. So if you're given a collection of fans and you count them, and then you say, okay, there are 28 fans here. So you will be able to abstract out from a physical collection of objects this notion of a number. And that number is going to be a unique label that you're going to assign your collection of objects. This is the meaning of saying that we are able to understand numbers at a certain level. So what does understanding mean in this particular case? What we are doing, so in the case of fans, etc., what you're doing is collections of fans can all be classified into this is a 1 fan or 0 fans, 1 fan, 2 fans, 3 fans, 4 fans, 5 fans, 869 fans, etc. So there are these nice clear dockets, and if you have a collection, you will be able to take out from that a fixed number which fits into exactly one of these dockets. That's what classification of collections of objects in terms of numbers means, and that's the same kind of idea that we'll apply to all locally two-dimensional objects. So in order to do this classification, this understanding, what we want is the following. I'm just repeating what I just said just at the end of the previous slide, but in more precise language. What we need is an exhaustive list, which means given anything, there is a list. Let's say that think of these as dockets. There's a docket with a so basically think of these as folders in your computer, maybe, or dockets, in the old system. So the first folder has a label 1 on it. The second folder has a label 2 on it. The third folder has a label 3 on it. The 869th folder has a label 869 on it. What do you do now? You are given now a collection of objects whose number you don't know. You count, and then you say it has, say, 59 objects. And then you say that, okay, this collection of objects then is assigned this docket 59 or this folder 59. So we need an exhaustive list with no redundant elements, which means what? If you had 2 folders marked 59, you wouldn't know which folder to put it in. So you need a list which is exhaustive, which means given a surface. Now let's come back to our original problem. We want to classify surfaces. So an exhaustive list, which basically tells us that given a surface, there is a docket, there is a folder in which you can put it. 1, that means it's exhaustive. This is the meaning of exhaustive. Second, it's not got redundant elements. So there is a folder in which it belongs, and there exists exactly one folder in which it belongs. That's the meaning of no redundancy. So this is the first thing. So you need such an exhaustive, non-redundant collection of dockets or folders. Second, what else do you want? What did we do in the counting case? We had this algorithm. We had a capacity to count 1, 2, 3, 4, 5, 6, and when that counting finishes, you get the right number. This was our method. So we want a similar method here. Given a locally two-dimensional object or a surface, we need a method to say which exact object in that list it is, which precise docket it belongs to, which precise folder it belongs to. So implicitly, we need to have a way of saying when two surfaces are the same. When are two collections of objects the same? When basically we count in terms of numbers, we count and then we say, okay, look, this is the collection of numbers in this collection. This is the number of objects in this collection. So there are 28 apples, 28 oranges. Both are assigned to the docket 28. This is the human capacity for abstraction. Yeah? 28 is what is common to 28 apples, 28 oranges, and that's the docket that we assign it to. This need not be physical, but in our heads, this is exactly what we are doing. And we need a very similar thing in order to understand surfaces. That's the problem that we are after. Okay, good. So we understood to some extent what surfaces are. Second, now we have at least a framework in terms of which we are going to understand. Okay, good. So let's get back to these surfaces. So we started off with this picture of a globe, and you look at a little square patch on it. Yeah? And you'll see that this is exactly the kind of thing that is taken out, and then it's made into a little patch of paper where we draw a map. This is exactly how we draw maps of parts of the globe. That's what's happening here. Yeah? That's what is allowing us to say that the surface of the Earth is locally two-dimensional and we can represent it as maps. So I've referred to this before. Let's go ahead. Now we look at a shape which looks ostensibly quite different. Let's say the surface of this rabbit or these pairs of rabbits. But you look at a little patch on its body, and then you have this and you take it out from there. Yeah? You abstract it out, and then what happens is that if you look at it closely, it looks like this little rectangle that we put on the top of this page. So which means that the surface of the rabbit also is a surface. Yeah, it's a locally two-dimensional object. For the rabbit also, if an ant was crawling or a bug was crawling on the rabbit, and if it was capable of drawing maps, then this is how it would draw the surface of the rabbit. The bits and pieces of the surface of the rabbit could be mapped out. Yeah? So that's how we draw maps. Yeah. So the map of the Earth, and here the map of the surface of the rabbit. Okay, good. Now, so we started off by saying that we'll understand locally two-dimensional objects, but what did we actually do? Let's go back to these two pictures before coming back to this problem again. Here on this Earth, there was this little square which we could map to a flat piece of paper with, say, coordinates, like graph paper. The same thing was applied to the rabbit. Think of the y coordinate as slightly tilted and the x coordinate as slightly tilted, maybe at an angle of 30 degrees to the usual x-axis. And what has happened is that you've drawn the surface of the rabbit, and you've drawn this grid in which a part of a patch of this rabbit fits. Yeah? So these are the axes along which you map a little piece of this rabbit. Yeah? Which means what? What we are really doing is mapping bits and pieces of the surface of the object that we are trying to study to a flat piece of paper equipped with coordinates, basically graph paper. What is that? That is a model of R2 in Cartesian coordinates. Yeah? So a formal definition now we have, so the second level of abstraction, so we started with this very crude notion, start with all visual information. Second, we started abstracting out, and we said something like locally two-dimensional objects, but now we want to make it even more precise so that we can manipulate it mathematically. So a surface, and mathematicians call these two-dimensional manifolds, where 2 stands for this locally two-dimensional. It's a topological space, which means it's a space. For those of you who are familiar, just think of it as a space equipped with some distance, which is locally homeomorphic to R2. Homeomorphic means it's a way of saying they are the same, in a certain specific sense. What this word means, we'll come to a little later. Locally means that every point has a little patch around it, and from that patch to R2, there is a bijective correspondence, which is both continuous and its inverse is continuous. That's the meaning of saying locally homeomorphic to R2. What you did was you looked at a part of the surface of this rabbit and you mapped it to a chart paper. Now, all the surfaces that we've been seeing so far, they have been basically nice, round, spherical, etc., etc. Question is, are there other examples? Are there other examples of surfaces? Other examples of things which are locally two-dimensional? And the answer is most certainly yes. Here is an example. What is this? This is a surface of a bicycle tube, yeah, or a surface of a donut. Yeah, so mathematicians call this a torus. Yeah. So here also it's been marked into a grid. So you looked at one of these small little rectangles, cut it out and put it on a piece of paper, and what you're going to get is again a chart. So if we were living on a globe that was actually torus shaped, we could again draw maps of it, except that globally it is a torus, but we don't know the global shape. Locally, it is just like these little rectangles here. We can cut those out and put them on paper, and that's going to give us a map of this torus. Yeah? So this gadget also has an atlas consisting of maps which are locally two-dimensional. So now we have at least two examples: the surface of a sphere, the surface of a torus, yeah, or a bicycle tube. Are there other examples? And we have to make more precise. I said that we want to say that two surfaces are the same if they are homeomorphic. So let me try to elaborate a little bit on, I've already given this definition, but let me come back to this definition one more time to say when two surfaces are the same. And so we say that two surfaces are homeomorphic if there exists a one-to-one onto continuous map from the first surface to the second surface, such that the inverse map is also continuous. Okay, this is the formal definition that we had given when we said what a two-dimensional manifold was. Every point has a little neighborhood homeomorphic to R2, which means it has a small neighborhood which can be mapped bijectively to R2 with a continuous map with a continuous inverse. So what does it really mean? Intuitively, how are you going to think of it? Intuitive idea is that the first surface can be continuously deformed to the second surface without tearing, without gluing. So what is a continuous deformation? So here is say a dumbbell with 3 bells, yeah? So there are these 3 bells. Then you start deforming it. What happens is that the middle fellow starts becoming a little thinner, and then finally at the end, it has become, after deforming this continuously, it's become again a nice sort of an elongated sphere. And then you can press the two sides together and it's going to be again a sphere. So this surface of this dumbbell that we started off with is homeomorphic to a sphere. This is one example. Let me give another example. You have a surface of a lemon, let's say, which is very crinkled, and then you start smoothing it out. And then at the end, you have a nice, round, smooth lemon. Yeah. So these are examples of what homeomorphisms are. So what is, let me just summarize it one more time. What is a surface? Something that is locally homeomorphic to R2, which means every point has a small neighborhood which can be continuously deformed without gluing, without tearing, to R2, flat piece of paper. And when are two objects the same? When are two surfaces the same? If they are homeomorphic, if one can be deformed to the other continuously without tearing, without glue. Fair enough. So we have the objects that we are trying to study. We have a notion of equivalence, namely homeomorphism. Yeah, the objects are surfaces, locally homomorphic to R2. Notion of equivalence is homeomorphism. Yeah. And now we want to say what is the classification of these problems? So the problem now is classification of all two-dimensional objects, all surfaces. Very good. So now let me give a quick sort of an exercise. You have, say, this is like a fidget spinner, yeah, or what is it called? A pretzel. So there are these three horns, and there is some stuff in the middle, and there are these three things here. The third one is like a teapot with three handles, except that it's closed, so you can't quite drink tea from it. And there's one where all the holes are arranged straight. Question: are these the same? Are they homomorphic? Are they different? So let me click a few times, and the answer is they're actually the same. They are homomorphic to each other. What was the notion of homomorphism that we had? One can be continuously deformed to the other. So how do we deform the first to the second? So imagine this whole thing is made of plasticine, yeah, some very elastic object. So then we stretch this out, take the two ears that are there on the left side, and we stretch them out, yeah, and then take this middle guy and slide it in. What do we get? We get the second picture, maybe flipped by 45 degrees or 90 degrees, but that's what we get. Yeah. So the first picture and the second picture are the same. They can be deformed to each other. Therefore, they are homomorphic. What about the third picture? Well, all that you need to do is take this fat part in the middle, the teapot, and flatten it. It's as if the fat part, these three teapot handles attached to it, and that's what's this third picture. So the third picture and the first picture are homomorphic. They are the same. The first picture and the second picture are homomorphic. Those are the same. So the first, and if two fellows are the same, then, and the one is same as the third, then all three are the same. So all these three pictures, though they look very different, they are actually the same surface up to homeomorphism. This is the technical language that we use, that they are same, but the word same is vague. We want a precise notion, so that's why we use the word homeomorphism. So these two fellows are same in the sense that they are homomorphic to each other. Okay, so that's the notion. Good. And let's look at this third picture. So it has, so what is a sphere? A sphere is a sphere with zero handles attached. So these are called handles, yeah? Just as in a teapot, they are called handles, yeah? So these are handles. So what is this? This is a sphere with three handles attached to it. The torus is like a sphere with a single handle. There is a joke that topologists cannot distinguish between the surface of a donut and the surface of a cup. You can move between one and the other. So that's a torus is a sphere with one handle. A sphere is a sphere with zero handles. This object is a sphere with three handles. So then here is a collection: sphere with zero handles, sphere with one handle, sphere with two handles, sphere with three handles, sphere with four handles, sphere with 59 handles, sphere with 869 handles, and so on and so forth. Yeah. And here is a remarkable theorem. This actually classifies all surfaces with a little qualifier. Take any closed orientable surface. I'll say what this word orientable means. We haven't come across it so far. What is closed? Closed means that it occupies a bounded amount of area in this three-dimensional space, say. And it does not have edges. So in earlier times, our ancients used to think that if we go to the end of the earth, we shall fall off. Well, that's not the case. The earth is round, so we don't fall off the earth. There is no edge of the earth. There is no edge that we'll fall off from. So we can go round. So there is no boundary. Yeah. So there is no edge of a surface. So that's object which does not have an edge and occupies a bounded amount of region in space is called closed. That's a closed surface. Orientable, we'll just say what this means a little later. But if you look at all closed orientable surfaces, each one of them is exactly one of these objects we started off with. It is a sphere with n handles for some non-negative integer n. N could be 0, 0 is not negative, 0, 1, 2, 3, 4, etc., etc. So you look at all natural numbers, add on 0, and that classifies all closed orientable surfaces up to homeomorphism. So all these examples that we are giving before, they are they are typical. All surfaces now can be brought into correspondence with positive integers union 0. There's one word that we have left unaddressed. What does orientable mean? And orientable means it has well-defined sides. Yeah, there is one side and there's the opposite side. What does that really mean? Let me give you a picture. Here is a painting by a famous painter called Maurice Escher. Yeah, many of you might have seen the stuff on which the ants are crawling. This is called a Mobius band. Yeah, a Mobius band is not orientable. Why? So imagine the first ant, yeah, the topmost ant, and think of its middle legs as a normal direction pointing out of the surface. So you follow this ant, and then there's this other bunch of ants that come along, and then finally it ends up on this last ant. So if you look at it, put a finger here, assume it's moving up, then this ant starts moving along the surface of this Mobius band, then it goes all the way around, and it has come back to this other ant, which is a little behind where it started off with, but it's on the opposite side, which means you start off on one side and you come back to the same point. If this lower ant, the bottom ant, moves a little forward, it will come back to the same point where it started off with, but its legs will be, the middle leg will be pointing in the opposite direction, which means this normal direction with which you started, and you've traced it out with your finger, and you've come back to the same point. The base of your hand, the base of the finger is at the same point, but it's pointing in the opposite direction. Yeah. In other words, there is no well-defined side to this object. Yeah? So you can go around, trace your pen, and you start off with one direction, you end up in an opposite direction. Yeah? That's what is happening here. Yeah? So a Mobius band is an example of something that is a non-orientable surface. So what is an orientable surface? Say, for example, a sphere. You start off with the North Pole, you go around any which way you like, and you come back, and you're going to come back to the North Pole with your finger pointing in the same direction. That is called orientability. Okay, so that's really what this is about. Yeah. So this is an example of a non-orientable surface. Let me quickly give you a couple of more examples, which are slightly, I mean, this is called a Klein bottle. It's essentially, okay, this is not going to be very important for what we are going to say further, but there are other examples. So this is like a bottle, but it's cut itself. So you can't quite say that this is a surface. I mean, this place where it cuts itself is not quite, does not have a locally two-dimensional chart to it. But you can make this into locally two-dimensional by a slight modification, which I don't want to go into. But the objects that we were studying in this theorem, yeah, oops, yeah, these are not these guys. There is a classification, very similar classification of non-orientable closed surfaces as well, but this particular theorem is what classifies closed orientable surfaces. And what have we done? We've said that it's a sphere with n handles, n ranging from 0 to infinity. Yeah, 0, 1, 2, 3, 4, all the way up to infinity. Okay, good. So we have now understood at least a vast collection of surfaces, namely the closed orientable ones. This part of my talk refers to shapes of surfaces. Yeah? So shapes refers to the subject called topology when two objects are regarded as the same if they are homeomorphic to each other. So they are the same if they are homomorphic to each other. And then you have a complete classification of closed orientable surfaces. They are spheres with n handles. But now let's go back to where we started. We started with this picture of a rabbit. Nobody in their senses would say that the rabbit and the sphere are the same, right? So where exactly is the difference? One is that the rabbit has sharp pointed ears. The surface of the earth is nice round. How do we capture this extra piece of information? And that's where geometry comes in. So there's more. These shapes are different, but at a slightly subtler level. So a rabbit is a sphere as far as topology is concerned, but a rabbit is not a sphere as far as its geometry is concerned. So how are we going to capture geometry? When we take one feature out, geometry is captured by curvature. Okay? So what is curvature? How are we going to understand curvature? So the tip of the ear of the rabbit is very pointy. It's not like the round, smooth surface of a sphere. That sharpness of a point is exactly what determines curvature. This intuitive notion, this rough notion of sharpness of a point is what captures curvature. So let's give concrete examples. These are examples of what are called Platonic solids. Yeah? Each of them, if you assume that it's made of some rubbery material, something like a balloon, yeah, then you can blow up each of these, and each of them is going to be like a sphere. Yeah. So how are we going to capture curvature? How are we going to capture the sharpness of a point? How are we going to capture the pointedness, the sharpness? That's where we need a precise quantitative notion of curvature. A precise notion of curvature is necessary. How do we get that? So the surfaces of all these solids is homeomorphic to a sphere, but the curvatures at the vertices are different. And let's go back to this picture. If you take one of these objects and poke yourself with it, then it's fairly clear that the tetrahedron, this little object here, is going to have the sharpest point. It's going to hurt most. And maybe this icosahedron, which has so many more sides, is going to hurt less. The sphere will not hurt at all. It's not going to pierce your skin. Yeah. How do we capture that? So we need a reference object or something which is not curved at all. And so the flat two-dimensional surface, yeah, flat R2, yeah, where what is happening? The flat R2, now think of it geometrically, not something that can be bent. Just say the flat tabletop. The flat tabletop is going to be our reference point. It does not pierce at all. So that object is what we refer to as our base object, which has curvature 0. Yeah? Which means what? That the sum of the angles around a point there is 360 degrees. It's 2 pi. The defect from that, the difference from that, is what measures curvature at a vertex. So how do we measure curvature at a vertex? Here is the quantitative measure. You take 2 pi and subtract out the sum of the angles of the faces that come and hit that vertex. That's going to be the curvature concentrated at that vertex. Let's do a quick example by going back to these pictures, and then we'll go to the next slide and do something else. Okay, no, maybe let me just go forward and do it with an interesting but not very difficult example. So let's look at this regular dodecahedron. Yeah? Each face is a pentagon. How many faces are there? So you have this first one, then you have 1, 2, 3, 4, 5. The next one, again, another 5. And then there's the back face. That's why it's called a dodecahedron. Dodeca means 2 plus 10, 12. So there are 12 faces. How many vertices are there? In the first face, there are 5 vertices, right? Then at the second level, there are another 5 vertices, yeah? And at the third level, there are another 5. And finally, there are another 5. Yeah, so there are total number of vertices. If you count this carefully, you are going to get 20 vertices on this dodecahedron. Yeah, that's what this is about. So the total number of vertices of the dodecahedron is 20. Yeah, okay, good. Keep that number in mind. It's going to be useful now. Okay. So what is the angle? What is the, let's go back and look at this. what is the angle at each of these vertices. So what is the total angle? It's going to be the internal angle of a pentagon plus an internal angle at a pentagon plus an internal angle at a pentagon. This is the total angle around a vertex, right? So they are flat pieces of paper. Each of them is a pentagon. 3 of them are pasted at a vertex. How are we going to compute curvature? We are going to take 2 pi, subtract out the total flat angle around this vertex, and that's going to give us the curvature concentrated at this vertex. Okay? So what is it? So what is the internal angle of a pentagon? How are we going to compute that? Well, we know something, basic thing that we learned from Euclidean geometry in school. The sum of the external angles is 2 pi. The sum of all the external angles is 2 pi. So how many external angles are there? 5 of them. So what is the average? What is each external angle? Is 2 pi divided by 5. Yeah. So then what is going to be the internal angle? It's pi minus 2 pi by 5, which is 5 pi minus 2 pi divided by 5, which is 3 pi by 5. So the internal angle of every pentagon, every regular flat Euclidean pentagon, is 3 pi by 5. This is sort of class 6, 7 geometry, yeah, Euclidean geometry. So then what is the total angle around a vertex? It's 3 pi by 5, 3 pi by 5, 3 pi by 5. Why? Because there are 3 of these faces at every vertex. So total angle around a vertex is 3 into 3 pi by 5, which is 9 pi by 5. So then what is the curvature? It's the defect from a flat guy. It's 2 pi minus 9 pi by 5, which is pi by 5. So the curvature concentrated at every vertex is pi by 5. 2 pi minus 3 into 3 pi by 5, which is pi by 5. Good. So at every vertex, we have total curvature pi by 5 concentrated. What is the total curvature then? Now you sum over all vertices. Remember, how many vertices did it have? 20 of them. So total curvature is 20 times pi by 5, which is how much? 4 pi. Okay. So for the dodecahedron, the total curvature around vertices summed over all vertices is 4 times pi. Let's go back to that picture one more time and do the same computation for some of the easier examples. Take the tetrahedron. What are the sides of the tetrahedron? They are equilateral triangles. What is the internal angle of an equilateral triangle? 60 degrees, pi by 3. So in this tetrahedron, how many faces are there around a tip? 3 of them. So what is the total angle? Pi by 3 plus pi by 3 plus pi by 3. How much is that? Pi. So what is the total angle around a vertex? Pi. What is the curvature? 2 pi minus the sum of the angles. So 2 pi minus pi, which is how much? Pi. Yeah. So what is the sum? So curvature at every vertex is pi. But how many vertices are there? It's a pyramid with a triangular base. So there are 4 vertices. So what is the total angle defect? 4 times pi, 4 pi, which was the same number that we got in the tetrahedron. Let's do it for the cube. What is an angle at a vertex? 90 degrees. Yeah, pi by 2. How many faces are there to a vertex? 3. So what is the total angle at a vertex? 3 times pi by 2. What is the curvature? 2 pi minus 3 pi by 2. How much is that? Pi by 2. How many vertices are there? 8. So 8 into pi by 2 is the total sum. How much is that? 4 pi. So a little bit of black magic is going on. Every time, however, whatever be the shape, when we take the curvature at every vertex, it's coming out to be something very different from, so here it's pi, here it's pi by 2, here it's pi by 3, pi by 5, etc., etc. But when we sum over everything, we are getting 4 pi every time. This is a theorem. So the fact is, you don't even have to have a regular triangulation. You just decompose your sphere into flat cells. And then whichever way you look at the sum of the angle defects, the sum of the curvatures, it's going to give you 4 pi. This is a very special case of a theorem called the Gauss-Bonnet Theorem. So the Gauss-Bonnet Theorem is true for every object, yeah, every closed orientable surface. Take any sphere with n handles, give it a cellulation, give it a decomposition into flat Euclidean pieces, yeah, polygons. And then you look at the curvature at every vertex, sum over that. And what you're going to get is 2 times n minus 2 multiplied by minus 2 pi. So when n is equal to 0, you're going to get the sphere. So that's minus 2 into minus 2 pi, which is 4 pi. So what we illustrated right now is that the total curvature of a sphere equipped with a cellulation, this is called a cellulation, division into cells, is always going to be equal to 4 pi. It's not just for the sphere. If you have n handles, then it's going to be minus 2 pi times 2n minus 2. Which means what? That the total curvature depends only on the number of handles, nothing more. Yeah. Yeah. So this n, the number of handles, was something that was the classification of topology. What this theorem, the Gauss-Bonnet theorem, says is that the total curvature is a topological invariant. Locally, curvature is different. Locally, geometry is different. But globally, sum the curvature and you get something that is an invariant of topology. Okay, I'll stop here. Thank you.
Priyanka?
Thank you so much, sir, for sharing knowledge with us. If anybody wants to ask any question from sir, you are free to ask.
Yeah, please go ahead. If anybody has any questions, please go ahead and ask.
Sir, there is one question from a student that Deepak Patidar sir को unmute कर दूं. Patidar sir पूछना चाह रहे हैं.
हाँ जी, अनम्यूट कर दीजिए. हाँ भाई,
जी सर.
पूछो भाई.
सर नमस्कार सर. सर
हाँ
आप
जी.
मुझे सुन पा रहे हैं?
हाँ
सर
सर,
audible?
आप बताओ. हाँ जी, बताओ.
हाँ सर. Sir, I want to ask something for dimension related. If you are saying, sir, it is probable the dimension is 7 dimension and 6 dimension and 4 dimension. This x, y, z is considered and t is also defined. But more dimension is possible for in future. Sir, you understanding what I am
फ्यूचर क्या
asking?
भाई? हाँ बिल्कुल. फ्यूचर में क्यों? अभी भी है. फ्यूचर में जाने का जरूरत नहीं है.
So sir, how can to predict
आपका,
the?
अरे भाई आपको लेटर चाहिए ना, तो आपको तो अंग्रेजी में 26 लेटर है. तो एक
Yes,
एक्स वाई जेड टी क्यों लगा रहे हो? एक्स वाई जेड डब्ल्यू यू वी जो भी लगाना चाहो लगाओ. हाँ.
Not sir, I am
तो
not
ये
asking
हम
this
नहीं
question.
करते. अरे नहीं यार, सुनो यार.
Yes.
तो आपको कोऑर्डिनेट लगाना है, तो आप उसको x1 x2 x3 x4 कर दो. ठीक है, तो 4 डायमेंशन मिल गया. x1 x2 x3 x4 x5 x6 x7 x8 8 डायमेंशन मिल गया. जितना आपको चाहे आप कर लो. R8 तो है ना आपके पास, R2 है, R3 है. कोई तो किसी ने बताया नहीं कि भाई यहां तक खत्म होना चाहिए. Human beings in the earth, on the surface of the earth, we see 3 dimensions at most, yeah, and maybe sees 2 dimensions. But that is just a restriction of our physical senses. या आप abstract कर लिए तो आपको जितना dimension हो चाहो करो. So there are 2 dimensions. I have talked about 2-dimensional manifolds or surfaces here. Similarly, there are 3 manifolds. 3 manifolds are manifolds, which means topological spaces where every point has a small neighborhood locally homeomorphic to R3. That's a 3 manifold. Something that is a 5 manifold will have every point has a neighborhood homeomorphic to R5. Similarly, R6, R7, R8, and you're going to get 6 manifolds, 7 manifolds, 8 manifolds, etc. ठीक है? जितना dimension 869 dimensional manifold भी आप कर सकते हैं. ठीक है?
Okay, sir. Got it your point. Okay, thank you very much.
Thank you, sir. Priyanka.
Now I would like to invite Dr. Rekha Jain, HOD Mathematics Department, Medicaps University, for the vote of thanks.
Thank you, Priyanka. I, Dr. Rekha Jain, HOD Mathematics, on behalf of Mathematics Department, Medicaps University, and on my own behalf, extend a very heartfelt thanks to our esteemed guest, Dr. Mahan, for sharing his valuable time and provide lecture on shapes and geometry. Sir, in very easy word, you have taken a complicated topic, and it is very much easy to understand the topology if teachers like you is going to taught us. Thank you so much for your time and for your sharing. I would also like to express a big thanks to our Honorable Vice Chancellor, Dr. Patnaik, for all his support and motivation. Thank you, sir. I am also very grateful to our Prof. Vice Chancellor, Dr. D.K. Panda, for his guidance. A special thanks to Director TIFR and Dr. Ganeshan, sir, for his valuable support for conducting this lecture. Thank you so much. Well, a weekly event like this cannot happen overnight. The wheels start rolling weeks ago, and I have been very fortunate to have a dedicated colleague of mine who have made all the efforts to make this event successful. In this reference, I would like to thank our co-convener, Dr. Rinku Verma and Ms. Dipali Biniwale, and our host, Ms. Priyanka Sisodia. Thank you so much. I would also like to thank our technical team for all their supports. A special thanks to our sponsor, National Council for Science and Technology Communication Delhi and MP Council of Science and Technology Bhopal for giving financial aid to us. Last but not the least, my dear student, to listen the lecture patiently. Thank you so much. Dr. Mahan sir, thanks again. Thanks for sparing your valuable time with us. Thank you so much.
Thank you, sir.
My pleasure. Thank you. Yeah.
Thank you, sir.
Okay, I'll
Thank
leave
you,
now.
sir.
Thank you. Yeah.
Thank you so much, sir.
Thank you, sir.